تعالى كده النهارده هنتكلم على البي اي تي سكانر او آه، ما يسمى البوزيترون اميتر توموجرافي. في الوهلة الأولى كده هتحس إن الشكل بتاع البوزيترون اميتر توموجرافي هو شبه السي تي سكانر وشبه الماجنتيك ريزونانس ايميجينج بالسيركل الكبيرة اللي أنت بتدخل جواها. هي way to take an image ولكن mainly to measure the radioactive activity level of an organ. يعني for an example لو أنا كشخص شاكك إن يكون عندي تيومر وعايز أحدد هل التيومر ده لا قدر الله كانسر ولا تيومر عادي، فوجدوا إن التيومر اللي بيكون نتيجة كانسر أو خلل في التيشوز هو بيكون الراديو اكتيفيتي بتاعته عالية أو النشاط الإشعاعي ليه بيكون أكبر بكتير. بس how to measure this radioactivity level؟ تاني يبقى أنا هستخدمه to measure the radioactivity level. يعني for an example لو أنا عندي brain tumor والتيومر ده أنا عايز أعرف هو كانسر ولا لأ. قال لك الكانسر سيل بتتميز إن الراديو اكتيفيتي بتاعتها بتكون عالية. راديو اكتيفيتي very high. طيب ازاي اقدر ان انا بقى اختبر الراديو اكتيفيتي بتاعت ده؟ قال لك عن طريق ان انا اعمل لها ايميجنج او ان انا اصورها باي ايميجنج، ولكن انا عايز صورة تكون بتوضح لي the different levels of radioactivity inside the organ as the brain مثلا، عشان اقدر احكم اذا كانت الاكتيفيتي هنا عالية ولا لا. وادام انا عايز اعمل imaging to show the radioactivity level فاستحاله هعملها من خلال الاكس راي العادي او السي تي سكان او حتى من خلال المagnetic resonance imaging، لان دول بيدوني contrast of colors to show that the tissue is soft or hard عن طريق البلاكنينج والوايتنينج، لكن ما بيدينيش degree of radioactivity. So we cannot use in this case all the other imaging machines. But how we can take an image to show the radioactivity levels inside an organ؟ قال لك عن طريق حاجة اسمها positron emission tomography. اللي هو ازاي ده؟ قال لك مبدئيا أنا محتاج أعمل 3 حاجات. محتاج إني أحضر تريسر والتريسر دي تكون biologically. يعني إيه مش فاهم؟ يعني لو تفتكر في الريزونانس magnetic resonance imaging كنا بنقول in order to increase أو حتى في السي تي سكان المرة اللي فاتت وإحنا بنشرحها قلنا you can inject the patient by iodine أو barium sulfate tablets in order to increase the contrast وأشوف الألوان بشكل أوضح. أهو الأيودين أو الباريوم سلفيت ده يعتبر تريسر لأنها حاجة absorbed by the organ and moves inside the blood stream فمن خلالها أقدر إن أنا لما آخد الإيمج تكون more clear. أهو أنا عايز نفس الحكاية أحضر تريسر بس يكون biological and radioactive at the same time to inject the patient by this tracer. tracer ده هيكون مادة يا إما sugar يا إما بروتين، ولكن التريسر ده البيولوجيكال اللي احنا قلنا ممكن يكون شوجر يعني أي حاجة من مكونات الجلوكوز أو even بروتين علشان الجسم يقبله ويحصل له absorption inside the brain. محتاج كمان إن التريسر ده يكون radioactive. طب ودي أعملها إزاي؟ قال لك عن طريق replacement of one of the molecules of glucose with a radioactive isotope as fluorine. وده بيتم تحضيره under the supervision of supervisor من خلال حاجة اسمها سايكلوترون. ايه السايكلوترون ده؟ يبقى أنا عندي ترم اسمه سايكلوترون. قال لك السايكلوترون ده هنحكي القصة بقى كلها على بعض. يبقى أول حاجة أنا محتاج إن أنا أعمل imaging للbrain tumor in order to see the radioactivity level and measure it and imaging it. So we cannot use the ordinary imaging machines. Instead, we will use positron emitter tomography. But at first, we need to prepare a tracer, a biological tracer, from sugar or from protein in order to inject the patient with it and absorb it easily by the brain. But this tracer must be radioactive. Why? Because we measure the radioactivity. So if we inject it by a normal tracer, no radioactivity difference will happen. The same as yesterday, when we said, in order to capture a photo of your face, I have to make two sources of light facing your face, right? If we have only one source, مش هتقدر تتصور. وعشان كده لما تدخل عند حد في استوديو تصوير تبدأ إن هو يشغل لك أكتر من فلاش لايت على وشك علشان يعمل difference ما بين الليفلز of lightning فيقدر يوضح الديتيلز بشكل صح. The same here, we need to measure the radioactivity level. So we need a difference in radioactivity. So we have to inject it by a radioactive sample. But this sample must be safely absorbed by the brain. So it must be a biological tracer. So how we create this biological tracer? Like inside a cyclotron. The cyclotron has two functions. The cyclotron is a type of accelerators. In order to accelerate the ordinary atoms, add oxygen. So we bring oxygen, which is 816. Then, by using the cyclotron, we started to converting it to fluorine 819. which is radioactive. يبقى أول way أو أول حاجة السايكلوترون هيبدأ يعملها إن هو convert by the high speed rotational motion of oxygen 816, the ordinary one, the staple one, gaining more energy to become fluorine 819, which is radioactive isotope. Sorry, 918. Fluorine 918. This is a radioactive one.
Okay.
Then we will bring the glucose. The glucose molecules, which consists of carbon, hydrogen, and oxygen, with different structures. We will replace one of the hydrogen atoms. Replacing. وهحط مكانها فلورين 918. فيتحول الجلوكوز من كونه جلوكوز لحاجة اسمها فلورو دايوكسي جلوكوز. أصبح عندي tracer radioactive biological جاهزة to inject. So this is called a chemical modification. And this has happened before taking the image by a few hours. So these samples have a very short time radioactivity. So the half-life time for fluoro 918 is very short in order to be safe. So you have to create and prepare this sample of tracer before taking the image just 1 hour or half hour. Why? Because it has a short time radioactivity.
Sir, we replace the hydrogen or the oxygen.
So again, the first part is to prepare the tracer. What is the tracer? It is a chemical substance which we inject the patient with in order to safely absorb it by the tumor or the organ which we need. And by the way, it differs according to the organ. So we can use carbon 11, nitrogen 13, but this is just to measure the radioactivity in the bloodstream, radioactivity in thyroid glands. So each organ inside our body need a certain type of tracer. But for the brain, they found that the fluorodioxyglucose is easily and safe to be absorbed by the brain tumors or by the brain tissues. So the first step is to prepare the tracer, a biological radioactive tracer, chemically modified. How? First of all, converting the staple oxygen into a radioactive fluorine isotope by using cyclotron. After that, we will replace a hydrogen atom from the glucose structure by this fluoro atom or isotope to convert it into a fluorodioxyglucose. Now, fluorodioxyglucose is a radioactive substance called tracer. So the first question always about this part, or the first title in the point that you have to cover, is define the tracer and what is the meaning of the tracer and how we prepare the tracer. So the tracer is a biological substance with a very short time radioactive, chemically modified in order to inject the patient with to be safely absorbed by the tumor or safely absorbed by the tissue. How we prepare it? 2 steps. First of all, we converting the oxygen 18 into fluorine 918 by using the cyclotron to become radioactive. But this radioactivity has a very short time. Number 2, chemically modification by replacing a hydrogen atom in a glucose compound by the fluorine isotope to convert it into a fluorodioxyglucose. So this is the tracer name, fluorodioxyglucose. Did we have more tracers? Yes. Depending on either fluorine or carbon 11 or nitrogen 13. But it depends on what? It depends on the organ we need to measure the radioactivity in. Now, the patient is ready. So we will inject it by this tracer, which have a very short half-life time. Great. The second step, the mechanism of the fluorodioxyglucose inside the tumor. Let's see. But first of all, there is any question about this part?
No, sir.
What the meaning of tracer? Please, if you have any doubt, just repeat it one, and we can search together, because this is the first time we examine this part in IGCSE. So if you have any doubt, imagine any question, you can see, and we can search together.
Okay, sir, but now it's okay.
Good. The second step is the mechanism. Now, if we have, this is the brain. So this is the brain. And we injected it by fluoro, again the name, fluorodioxyglucose. So the fluorodioxyglucose now is absorbed inside the tissues. And as the fluorodioxyglucose is a radioactive, so a radioactive decay will happen, right?
Yes.
Great. So the fluorine 918 will decay under the effect of beta positive decay to oxygen 818. It is the oxygen which is absorbed inside or dissolved inside the water. This is not an oxygen gas. Plus positron That's why we call that technology or the mechanism a positron emitter, because we need this positron. So after injecting the brain by the fluorodeoxyglucose, which is radioactive, it goes under the decaying of beta positive. So it is a beta positive decay to decayed into an oxygen 818, which is dissolved in water. Dissolved in water. And a positron. What happened for this positron? So this positron will meet inside the organ because of a lot of atoms inside the glucose itself, electron. What happened? A positron 0, 1 met an electron E -1 to 0. What will happen?
The electron is from where?
Matter and antimatter.
Sir, electron من وين?
So positron and electron having the same energy, the same charge, but in opposite directions. They will vanishing each other, annihilation. So annihilation happened.
Sir? Hello, sir?
But we call this is a collision. And this collision will result into what? Muhammad?
Vanish.
Great. So it will result into what? 0, 0, which is gamma. Great. Now we have gamma, but not only one gamma, we have 2 gammas. Why? Because as we said, this is a collision, and this is very, very important point. Why we have 2 gamma? They show that the effect of collision between positron and the electron resulted to gammas with same energy moving in opposite direction. So this is gamma 1 and gamma 2. But why? Because the total momentum before the collision must equal the total momentum after the collision. And as the total momentum here is equal to 0, so the total momentum after must be 0 too. So if we said that this gamma had an energy which is about 511 kilo electron volt, so the momentum can be calculated through this energy because E equal mc squared. So we can find the amount of mass defect of gamma, and either we can see that the momentum of the gamma is available. So in order to reach to total momentum equal to 0, it must emit 2 gamma in 2 opposite directions by the same value of of energy, which cancel each other. So they make the total momentum is equal to 0.
Sir, why المومنتم 0 في البداية؟
لأن ده عنده mass into velocity، صح؟
Yes.
وده عنده mass into velocity, but they are moving in opposite direction. So the total will be equal to 0. So the total momentum of positron and electron, because they are antimatter and matter, so they vanishing each other, so they resulted to 0 momentum. So we cannot say that the resulting of 0 momentum is equal to a momentum. So it must be 0 momentum. So it must generate two gamma with the same amount of energy in opposite directions. So again, by injecting the brain or the patient by the fluorodeoxyglucose, which is the biological tracer, a radioactive decay happens, a beta radioactive decay happens to the fluorine 918 into oxygen, which is dissolved in water 818, and a positron resulted, or beta positive. This positron emission undergoes another reaction with any electron inside. And the effect will cause to generate two gamma rays with same energy in opposite directions. Right? Now, the brain emit gamma. After this mechanism, we have how to detect this gamma. How to detect. Because we have for each reaction of positron, because we have a sample of fluorodeoxyglucose, so we don't have only one positron, we have a lot of positrons will generate. So we have many of gamma rays can produce in different direction according to the position of the sample inside. And the position of the reaction happened between a positron and the electrons. So we will put the patient brain or the organ which we need to image inside a circular ring. So this is a circular ring. Circular ring. Containing many of small Geiger counter gamma rays detectors. So the containing inside many of Geiger counter gamma ray detectors. So you can find that we covered all the ring. So if this is the patient tumor and it emits two gamma radiation in the two opposite directions, so this detector will start to detect the radioactivity timing. So the third part is how we can detect this gamma radiation. We can detect it through the circular ring, which contain many of small Geiger counter gamma ray detectors, which detect the gamma ray which getting out from one reaction only of positron and the electron, because they are in the same axis, opposite in directions. So this detector, which we call the A and B, will detect a gamma radiation which is getting out from one positron. Great. And another reaction can be happened here. So this detector and this one will detect the other gamma radiation called C and D. And another called E and F. So we detect a lot of gamma radiation with different positions to make something called a 3 dimensions different of activity. Why? Because the activity of this positron located at a certain area inside the positron will differ according to the reactivity of the organ itself Then another one located at different one. By mean, in the brain, we have this tumor and this cell and this cell and this cell. All of them absorbed the fluorodioxyglucose. Great. So a positron here will release and make a detection for gamma. And here, a detection for gamma. Here, detection for gamma. Here, detection for gamma. So if this organ or this tumor has a radioactivity level, which is very high, it will appear on the computer as a darkened color. So these readings of gamma ray detection will process into a computer to convert it into colors. The regions which have a high reactivity levels will appears in the form of darkened or blackened colors. And the regions which have a small amount or lower amount of radioactivity level will show with a lighter colors. So after being detecting, we computerized this difference in radioactivity measurement, which is measured by the gamma ray detector inside the circular ring and converted into colors. And a three-dimensional image or video can process. And from it, we can see if this tumor has a high radioactivity level or low, then we can see that if it is a cancer or not. After a while, this radioactivity of fluorodioxyglucose will disappear. So it is safe for the patient because it has a very short half-life time. So within 1 or 2 days, this radioactivity will release from it because it will emit a gamma radiation until the radioactivity vanishes. Do you have any question in this part?
No, sir. No.
Okay, we can see 2 videos for the P.E.T. scan, the shape of P.E.T. scan and how it's happened inside to imagine the, okay?
Okay.
Great. Okay. Yes. Yeah. It appears?
Yes, sir.
You can see the video?
Yes.
Okay. The sound is clear?
No, sir. مش سامع.
Now you can hear?
Yes, yes. Now I can.
Rather than details of its structure. To do this, short-lived radioactive chemicals are injected into the bloodstream of a subject or patient, and a ring of detectors maps the destination of these chemicals in the brain by sensing the emission of radiation in the form of gamma rays. Many of the radioactive isotopes used in P.E.T. are produced using a cyclotron. An accelerated stream of protons is directed at a stable target material, changing its atomic structure. To produce fluorine-18, a common positron emitter, the target material is O18-enriched water. During the bombardment, the oxygen-18 gains a proton and loses a neutron to become fluorine-18. The radioisotope is now incorporated into biologically relevant molecules. By far the most common tracer used in brain imaging studies is fluorodeoxyglucose, FDG, an analog of glucose. In FDG, fluorine 18 is substituted for a hydroxyl group. FDG is used in studies of brain metabolism to determine which areas of the brain are most active during a particular behavioral task. Because fluorine 18 can be substituted for hydrogen or hydroxyl groups in chemical compounds, it can be attached.
So it can be replaced by either hydrogen or hydroxyl group. Muhammad?
Yes, okay, sir.
Okay.
To a wide variety of molecules. For example, F18-fluoro-L-dopa is often used to study dopamine synthesis in the brain. Other commonly used positron emitters include oxygen-15, carbon-11, and nitrogen-13. The name P.E.T derives from the fact that these radioisotopes are unstable and decay by positron emission. When the nucleus of the atom ejects a positron, abbreviated beta plus, the effect is to convert a proton into a neutron, an event that stabilizes the radioisotope. Positrons are basically positively charged electrons or anti-electrons. The emitted positron travels only a short distance before encountering a nearby electron. The two particles combine and annihilate each other, resulting in the emission of two high-energy 511 kilo-electron-volt gamma rays in opposite directions. The gamma rays easily pass through the body and are detected by the electronics of the tomograph. Modern tomographs contain thousands of detectors arranged in rings surrounding the field of view. The tomograph software identifies gamma rays that are coincident, that is, those that are likely to have originated from the same annihilation event. By reconstructing the site of the positron-electron collisions, the concentration of the radioisotopes can be determined. In the reconstructed FDG PET image, areas of high activity and hence higher glucose utilization appear dark, while areas of lower activity are lighter. Researchers can also apply artificial color tables to the PET scan, facilitating the identification of regions of high activity. Note that these color tables can be either linear, for example from light to dark, or non-linear, where hotter colors are used to indicate increased activity. PET provides a useful tool for isolating specific brain activity. By acquiring scans under both experimental and control conditions, the difference in brain activity in the scans can be computed and represented as a color-coded difference image that shows the regions of the brain that were more active during the experimental condition. Because PET measures activity rather than anatomical structure, PET scans are often superimposed on MRI scans from the same subject.
So this is the difference between the two pictures, the MRI scan and the P.E.T scan. It shows more details, and this difference in colors appear the difference in radioactivity levels.
Make it easier to determine which structures are active. In behavioral studies, scans from the experimental group can be averaged and the activity of control group subtracted to reveal which brain regions are selectively activated.
لما يكون يعني بلاك يعني الراديو اكتف.
ايه؟
لما تكون الصورة بلاك يعني راديو اكتف.
Just 1 minute. تاني بقى محمد.
لما يكون الصورة بلاك يعني في راديو اكتيفيتي.
as more plaquing as more radioactivity emitted from this organ.
يعني إذا في colors يعني مش راديو اكتف.
لا، هو قال لك في البداية خالص ممكن أعملها black and white. ممكن نسمع الجزء ده تاني عشان برضو تبقى أنت هنا low activity by mean whitening أهو في الإيمج. High activity by mean plaquing. But the scientists developed this method in order to be more colorful. So they used, instead of the black in color, the hard color as. So the red and orange shows high radioactivity, while the soft color as green and blue shows low radioactivity. So either we can use the black and white images, or we can use high and low, hard and soft colors.
Okay.
And finally, you can find this. Where the other image? Yes, this one. This is the tumors inside the brain. You can see that this one has a low radioactivity. This is one has a low radioactivity, while this one shows a high radioactivity. While the other ones has no radioactivity, so it appears as MRI, black and white.
Oh. Okay.
Great. We have another video, I think, to show. Just give me 1 second. Yes. No. This one. Yes. Okay. You can see this video too. The sound is clear?
No, no, I can't see.
You cannot hear the sound?
No, sir.
Now?
Even no, no sound.
Still no?
في بس كتير واطي.
Okay, I'm trying.
Doctors will see Dave's brain at work. It's all possible because of tiny traces.
No, it is 100.
Specially designed radioactive molecules.
طب صار خلاص سعيدة إنه بركز بالصوت.
What?
repeat the video and بقرب أنا بسمع الصوت بحاول.
Okay.
Meet Dave. He's about to have a brain scan. Using the latest PET imaging technology, doctors will see Dave's brain at work. It's all possible because of tiny traces, specially designed radioactive molecules. The PET scanner tracks the position of the traces inside Dave, revealing his brain function in 3 dimensions. The traces don't come from a stockroom shelf. Each one has to be made fresh at a nearby laboratory. This is Dr. Miller. He's making the tracer for Dave's PET scan. First, he needs to produce the radioactivity using a device called a cyclotron. It smashes high-speed particles into ordinary atoms, transforming them into new radioactive atoms. Now the clock is ticking. The new atoms are giving off their radioactivity, becoming plain old regular atoms again. There goes one. It means Dr. Miller and his team have to work quickly to build the tracer, a biological molecule. This is what makes PET so unique. The molecule could be anything: a sugar, a protein, a hormone. Each one is tailored to a specific function in the body and will show doctors where in the body that function is happening. Dr. Miller's team runs special chemical reactions to create a tracer from a drug used in the brain. The new tracer must pass quality control. It is purified and checked that it will function properly. The tracer is ready to use. Good work, Dr. Miller. The precious custom-made molecule is rushed to the PET clinic. Just the right level of radioactivity is measured out. Then it's injected into Dave's bloodstream. There'll be a sharp scratch. It's not long before Dave's brain has absorbed the tracer and the clever chemistry gets to work. Inside Dave, an incredible reaction is taking place. The radioactive atom on the tracer loses its radioactivity, giving off a subatomic particle called a positron. It's just like the tiny negatively charged electrons found on all atoms, except that the positron is positively charged. So when the positron hits an electron, at just the right speed, they combine and destroy each other. The energy is released as two gamma rays that travel straight out of Dave's body in opposite directions. The P.E.T scanner is like a big ring of Geiger counters. When it detects two gamma rays on opposite sides of the ring, the doctors can calculate where in Dave's body the tracer must be. By detecting thousands of these events every second, and with some clever computer processing, Dave's brain activity is revealed in 3 dimensions, something no other imaging technique can do. For Dave, it was just a small injection. That wasn't so bad, huh? All made possible by the incredible technology of the tracer. The potential for P.E.T is enormous. Different tracers can detect cancer, heart function, and even track Alzheimer's. The P.E.T scan has revealed Dave's brain is functioning as it should. Dave, you're A-OK. In the next hour or so, his radioactivity levels will be back to normal. It's another successful job for the incredible tracers. But the work of Dr. Miller goes on as he continues creating new tracers to help those in need.
Okay. Muhammad? Muhammad?
Yes sir.
Muhammad?
نعم أستاذ.
Muhammad?
Yes أستاذ سامع.
Yes, Muhammad.
إيه.
Muhammad?
ألو.
You're
ألو.
in? Hi, Muhammad.
Hi sir.
Yes, great. The image was lagging and the sound too. Okay. So, from these 2 videos, do you have any questions?
No sir, actually no.
Okay, you can open the points that should we cover in this part, please.
Okay.
And we can see it together. I have this part. Let's see if we have. Okay. So first of all, understand that a tracer is a substance containing radioactive nuclei that can be introduced into the body and then absorbed by the tissue being studied. Recall that tracer that decays by beta decay is used in positron emission tomography, P.E.T scanning. Understand that annihilation occurs when a particle interacts with its antiparticle and momentum are conserved in this process. Explain that in P.E.T scan, positron emitted by the decay of the tracer annihilation when it interacts with electrons in tissue, producing a pair of gamma photon traveling in opposite direction. Calculate the energy of gamma ray photon emitted during the annihilation of an electron positron. We have to calculate this, but it is approximately 511 kilo electron volt, but we can, using the calculations, to find this energy, E equal mc squared. Understand that the gamma ray photons from an annihilation event travel outside the body and can be detected, and the image of the tracer concentration in the tissue can be created by processing the arrival times of gamma ray photons. So I think we covered all the points. Do you have any doubt about any point of this one?
No, sir, no.
Okay, so let's summarize again all what we said. We have 4 steps. First of all, with the meaning of P.E.T scan, it is a way to take a 3-dimensional images for a radioactivity difference levels inside a organ. PET by mean positron emitting tomography. Second of all, we need to create or prepare a tracer before injection or before taking the image a few hours. And this tracer is a biological tracer, a radioactive, chemically modified by making oxygen, the ordinary oxygen, turn it into a fluorine isotope inside a cyclotron. Then, by a replacement inside a glucose compound, we're replacing either the hydrogen or the hydroxyl group by the fluorine and turn it into a fluorodioxyglucose, which is safe to be injected and have a very short half-life time, so its radioactivity is not so harmful. After being injected by this substance, the brain or the organ which we need to image will absorb this material, and a beta decay will occur, which resulted into a oxygen 18, which is dissolved inside water, and positron embeds. This positron will move for a short distance before it interact or collide with an electron, produces an annihilation event, which causes a vanishing of the two particles and emitting two gamma radiation with the same energy moving in opposite directions, which can getting out easily from the brain. As we know, the gamma radiation has a high penetration power, so it can penetrate through the body and can be stoppable only by lead sheets. So it is easily moving out from the brain and detected by the cyclic or a ring inside and outside a circle, which containing many of Geiger counter gamma detectors. Then these detections will process during the computer and different color imaging showing a difference in radioactivity levels. The black in colors are for high radioactive, the gray and white color for the low radioactive, and the doctors can improve it to use colors as hard colors and soft colors, which is very, very useful instead of the magnetic resonance imaging. So any question this part?
No, sir, no questions.
Okay. I think we don't have even now questions on past paper for this part, but we can solve some questions about the nuclear radioactivity to be sure that we finished all the part of X-rays and medical physics. Okay, just give me 1 second. File Explorer. Yes. Okay. Yes. This one. Okay. 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 For 2021, question number 12. You can see.
No, sir.
Hamad?
No, sir.
Yes.
Yes, now I can see.
Okay. Let's start with atomic physics or quantum physics and X-ray part in 2021, then 2020, then 2019, then 2018. These 4 sessions. After that, we can solve the other ones. Okay. What's meant by a photon?
The quantum of energy when it's in the form of electromagnetic radiation.
Great. A stationary nucleus of samarium 159 emits a gamma ray photons of energy 0.57 mega electron volt. Determine for one gamma ray photon its wavelength.
Okay. E equal hc over lambda.
Great. E equal h nu, which is equal to hc over lambda.
So
Lambda will be equals to hc
over E.
Correct.
6.63 into 10 to the power negative 34 into 3 into 10 to the power 8 divide 0.57 into 1.6 into 10 to the power negative 13. So
Yes.
it's like 2.18 into 10 to the power minus 12.
Into 10 power negative 12. Yes. Which is approximately cam angstrom. This is in meter, and this is correct. But it must be between 200 and 400, something like that, in angstrom. So angstrom is 10 to the power negative 10.
So I'm going to divide 10 to the power negative
Times.
10 to the power negative 22.
We need from meter to angstrom, 1 over 10 power negative 10 times 10 power positive 10, or divided 10 power negative 10. Great.
So 0.0218.
0.0218 angstrom.
Yeah.
Very small. Okay, we can check this one. Okay, after finishing the momentum, we can check it together. The whole answers. It's a momentum.
Equal mv. اوكي ممكن لا الماس E equal mc square.
Right.
والv هي الفيلوسيتي تبع اللايت.
PL equal MC, right?
Yeah.
Okay, and M equal
E
over
c square.
C squared multiplied by C.
So 3E over C.
Right.
So 0.57 into 1.6 into 10 to the power minus 13 divide 3 into 10 to the power 8. So 3.04
3.04
into 10 to the power minus negative 22.
10 to the power negative 22. Okay. which is kilogram meter per second or Newton second. Okay. Using your answer to P2, determine the speed of the samarium 157 nucleus after emission of the photon. You have this equation. Samarium emits gamma radiation, and this is the energy. We need to calculate the speed of the samarium after emitting gamma radiation. So as 62, 157.
So is it the same?
Yeah, emit gamma, which is 0, 0. So it will be samarium also 62, 175, or two other which are having the same mass. Okay, so we need to calculate, determine the speed. So here we have the momentum, right? And momentum is equal to mv.
Yeah.
So the same momentum, okay, 3.04 into 10 power negative 22 equal to the mass of samarium multiplied by the speed, right? The mass of samarium is?
E over C square, so 0.57 into 1.6 into 10 to the power negative 13 over 3 into 10 to the power 8 square, 1.0 into 10 to the power negative 13.
What?
1 into 10 to the power negative 30.
1 into 10 to the power negative 30?
Yeah.
This is for what?
The mass.
Mass of gamma or mass of samarium?
Samarium.
Okay, V. So V is equal to 3.04 into
3 into 10 to the power 8.
3 into 10 to the power 8? I doubt. 10 to the power 8. By reference, explain quantitatively why speed of samarium may be assumed to be negligible compared with the speed of the photon. No, you calculate the mass of photon, not the mass of samarium. This is not the mass of samarium. Samarium is 157, right?
Yeah.
So it has 157 nucleon multiplied by 1.66 into 10 power negative 27, right?
So 2.6 into 10 power negative 25.
Into 10 power cam?
Negative 25. Negative 25.
25. Okay, so the velocity now is equal to?
ألف ومية ستة وستين point 45.
1166.5.
0.45.
Okay, meter per second. 245. I think now it is acceptable. We can see the marking scheme. Yeah, so by reference, explain quantitatively why the speed of the samarium nucleus may be assumed to be negligible compared by the speed of the photon. Although according to the value, there is a big difference between, because the mass of the photon is negligible, while the mass of samarium has a very massive nucleon, which is 157. So according to the values, there is a big difference. But let's see كده model answer. First. I think was page this is not the good. Yeah, I need the marking scheme. Okay. 12, question 12. Quantum of energy, and the first one, 2.2 into 10 power negative 12. It's correct, right? Can check. Yeah, 2.2 into 10 power negative 12, correct?
Yeah.
And the momentum was?
3.04.
Wait.
3.0.
3.0, let's see. Yeah, 3.0
Yes.
instead. Yeah, this momentum is equal to, so we need, this is the momentum. Yes, great. 1.2 into 10 power 3, yes, great. 1.2 into 10 power 3. Yeah, right?
1200 yeah تقريبا.
Yeah, 1.2 into 10 power 3, so it's correct.
بس كيف هو لقاها؟
Recoil equal 3 into 10 power negative 3 هي mass of some nucleus هي 1.177 into 1. زي ما احنا عملنا. or الماس 0.157 over 6.02 ديت بالمولز، بس لا احنا هنعملها بالنيوكليونز عادي. وبعد كده السبيد equals كذا اللي هو 1.2 into 10 power 3 المومنتوم over الماس. 1 is much less than, so all the questions correct. Okay, great. We can, let's see, 2020. I think the band theory is the band theory is cancelled, right?
Yes.
Okay, number B, structure of copper. We will solve number B and question 12. Structure of copper crystal is to be examined using electron diffraction. Electrons having been accelerated from rest through potential difference V are incident on the crystal. The de Broglie wavelengths of the electron 2.6 into 10 power negative 11. The de Broglie. Calculate the accelerating potential difference V.
Probably wavelength equal h over
Lambda equal.
time. H over momentum.
MC, right? L?
Yeah.
E squared over C by mean EC, right? So we will,
Hello.
yes. Mass electron into C. How we can use this one? Hamad? Hamad.
Yes, sir.
Yeah, okay. How we can use this relation to reach to the potential difference, accelerating potential difference?
Sir,
Yes.
I remember one equation, HC over electron volt.
Yeah.
Wavelength. Yeah.
So lambda equal HC over
Electron volt.
U.
So it is equal to, okay, we can find electron volt now. So electron volt equal HC over lambda. Yes, sir.
What?
Electron volt equal HC over lambda.
Yeah.
6.6 34. So electron volt equal 7.65.
7.65
into 10 to the power negative 15.
into 10 power negative 15.
So no drop of 1.6 into 10 to the power negative 19.
1.6 into 10 power negative 19.
1.224 into 10 to the power negative 33.
1.224 into 10
Power negative 33.
negative 33. This is the energy, so in joule, right?
Yeah.
We need the volts.
Okay, so volt equal work over charge. Huh?
So volt is equal to energy by mean over Q. So I think it will be this only, right? For negative 15. I doubt this is correct answer. You can check. Okay. Okay, this is question number 11, 11B. mv equal h over lambda, not ev, mv. So v equal, so this is velocity. After that, qv equal half mv squared. This is how he solved. 2.2 into 10 power 3. So first of all, instead mv, he used v and determined the velocity of the electron. And after that, the kinetic energy, E equal V into Q. So this is the velocity of electron, not 3 into 10 power 8. So again.
Oh, we used 3 into 10 power 8.
Yes. So first of all, again, use this question. Okay. So V electron will equals to H over lambda m electron. After that, we will find the energy of electron, which is half mv squared, not mc squared, v squared. Then we can find that energy is equal to qv. qv. So v equal to the energy which we obtained over k. 1.6 negative 90. Yes, Muhammad.
صار عملت calculation نفس الشيء 2.3 2.2 into 10 to the power 3.
Muhammad. Muhammad.
الو سر.
محمد.
الو سر سامعني؟
انت سامعني؟
Yes.
The image and sound are lagging. Wait. Now?
Now.
Yeah, it's great. It's great now, but the image is fixed. Can you hear me? Muhammad. محمد.
طب يس سر انا قادر اسمعك.
تمام، انا كمان دلوقتي سامعك. بس انا سامعك. محمد انا سامعك. What's happened?
Hello.
محمد.
Hello.
محمد.
Yes, sir. سامعني؟
The sound is lagging.
Hello.
Yes, I can hear you. أنا سامعك بس الصوت بيجي على مراحل كده. يعني الكلمة بتتقطع كذا قطعة.
Still. Hello.
محمد أنا سامعك.
سر شكله الصوت متأخر بوصلك.
تقريبا كده. محمد. 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 يا محمد أين أنت يا رجل؟
Hello.
محمد.
Hello. Yes, sir. سامعني؟
أنا سامعك كده تمام.
أوكي كويس.
أوكي great.
اوكي سر، عملت الكالكوليشنز وطلع صح 2.2 into 10 to the power 3.
أوكي yeah. The next question. يبقى هي الفكرة كلها إن ده velocity of electron not the velocity of light. State what is meant by the mass defect of nucleus.
Difference between the mass of the separated nucleons minus the mass of the combined nucleons.
Great. Some masses are shown in the table: mass of the proton, mass of neutron, and helium nucleus. Show that the energy equivalent of one atomic unit is 934 mega electron volt. I think we did it before several times, so no need to. Yeah, the binding energy per nucleon of helium-4 nucleus is 7.09. We solve it too.
So I think we solved this paper, these questions.
This question, okay, we can fix on the atomic part. Okay. Atomic part. Okay, this one. Yes. This is a continuation. This is about the ultrasonic. Okay. State what's meant by specific acoustic impedance of medium.
It is the the density into the speed. Yeah, specific acoustic impedance is the density times the speed of the incident.
Yes.
Ultrasound in the medium.
Great. A parallel beam of ultrasound of intensity I node is incident on the boundary between two media A and B. So this is specific acoustic impedance, and this is it has also a different The two media A and B have a specific acoustic impedance ZA and ZB respectively. The intensity of the beam transmitted through the boundary IT. State how the ratio IT of transmitted over I node of incident depends on the relative magnitude of ZA and ZB.
Okay, so our issue reflection coefficient equal Z2 minus ZB minus ZA square over ZB plus ZA the whole square.
Great.
So كل ما قل الريفلكشن coefficient كل ما زاد الترانسميتد، كل ما يعني ما زاد الريشيو.
Bravo.
والعكس صحيح.
Great. The linear absorption attenuation coefficient mu of medium B is 223 meter per to the power -1. Calculate the thickness of medium B required to reduce the intensity of the ultrasound beam to 34% of its initial intensity.
Okay, so I equal I node.
Yes.
I equal I node E negative mu X.
Mu X.
So the I node is 100, the I is 34.
I over I node is equals to
E
to the power
negative 23x.
23x.
So 34 over 100
Yes.
equal E.
We need to show that required to reduce to 34. So it will be 100 minus 34, right? Calculate the thickness required to reduce the intensity of ultrasound to 34% of each initial. So it will be 63 or 65?
66.
66, right? I think.
Yeah. So 66 over 100, right? Equal E negative. So then, so تطلع 0.018 X.
0.018 meter, right?
Yeah.
We can check. We can check. Okay. This is which question? This is 2019, right?
Yeah.
Okay. Mark scheme for 2. Okay, this is question number 4. Question number 4. Okay, question number 4. 0.047, no, you were correct. 0.34. You were correct. So I over I node is 34 over 100. Yeah. Calculate the thickness required to reduce the intensity to 34 of its initial, I mean 34 over 100. Yes.
0.047.
0.047. Okay. Attenuation noise is not measurable. Yes. Okay. State what's meant by a photon. I think we said it. Calculate the wavelength of the photon. And he had the energy.
energy equal hc over lambda. So lambda equal hc over E.
Right.
6.63 into 34 into 3 into 24 8 divided energy 1.18 to 1.6 into 24 negative 13. Like 1.05 or 1.1 into 10 to the power minus 12.
Minus 12. Okay. Show that the momentum of the photon is 6.3 into 10 power negative 22.
So for mass into velocity, so E over C. E over C لما نسوي cancel بالC mass.
C. No. MC. No. E into C, I said. PL equal MC.
E over C. Yeah.
MC. And M is E over C squared.
So C تحت تتكنسل مع اللي فوق.
Yes, E over C, great.
Okay, so تطلع 1.22
1.06 into 10 negative 12.
So non-energy 1.18.
Sorry.
1.18 into 1.6 into 13.
1.8 into 10 power
1.6 into 10 to the power
0.6 into 10 to the power negative 13.
over 3 into 10 to the power 8. يطلع الجواب.
Okay. Determine the recoil speed of the coupled nucleus when gamma ray photon is emitted. Yeah. So
Coupled 60, so 60 into 1.66.
So V equals to momentum, which is 6.3 into 10 to the power negative 22 over the mass, which is 60 into
1.66
1.6 into 10 power negative 27.
يطلع 6325 تقريبا 6300.
300. Okay. نشوف ده question number كام؟ 11. Okay. 6300 مظبوط. 6.3 into 10 power negative 22. 1.05. Yes. Correct. State what's meant by the binding energy of nucleus.
The minimum energy required to separate the nucleons of a nucleons to infinity.
Great. Calculate the binding energy of nucleus of lanthanum 144.
So
we have the mass here.
Yeah, we convert it to kilogram and then C square.
No, I think we have to find the mass defect as first. Because the binding energy equal mass defect times C squared. So delta M equals to the mass of the separated nucleons. We have here 57 protons times 1007 plus how many neutrons? 141 minus 57?
84.
84
Yeah.
into 1.009 minus 140.911.
Which 1.244.
1.244.
Yeah. So but this is the mass.
I thought that you finished it. Okay, multiply it by c squared. But we have to convert it at first into kilogram, right?
Yeah.
So 1.44 into 1.6 into 1.66 into 10 power negative 27.
Okay. Into c squared.
Yes.
يطلع 1.858
1.858
into 10 to the power minus 10.
only?
Yeah, into 10, no, into 10 to the power minus 8. Minus 10, عفوا, 10 to the power minus 10.
Okay. We can check.
Okay.
12. Mass effect, yes. 1.9 into 10 power negative 10.
Yeah, صح.
It's okay. Correct. The nuclide lanthanum has a half-life of 3.9 hours. Initially, a radioactive source containing only lanthanum, the initial activity is A0. Calculate the time of the activity of the lanthanum to be reduced to 0.40 A0. So A equal A0
E
the power negative lambda T, right?
Yeah. Yes.
And lambda sure it is 0.963 over half lifetime, which is 3.9 into 60 into 60, right?
يمكن هو مش طالب نحولها لأورز لسكندز.
ايه؟
هو طالب نحولها لسكندز.
طالب التايم، هو عايز التايم. فأكيد التايم عايزه لا بالأورز. Okay, so
Okay, بيطلع 0.1777.
0.177. Okay. يبقى A over A naught هو 0.40 A naught over A naught, صح؟
Yeah.
Okay, equal E to the power negative 0.177 T. دي راحت مع دي. ناخد then.
Okay.
Yeah.
Okay, so then 0.4
Equal
negative, so divide negative 0.177. 5.2 تقريبا.
5.2 hours. Let's check. 5.2. 5.2 hours. Great. Correct. Okay. The next question here. Suggest why the total activity of the radioactive source measured at the time calculated in 1 may be greater than 0.40. Initially, radioactive source contained only 144. After decaying, it brings more
nutrients, so more chain reaction.
daughters. We call it daughters nucleus, or by mean if the uranium can decay it into 2 or more daughter nucleons, which take more time. I think it is about the uranium 236. It released two, right? Polonium not 1. And krypton, so I think this is because 2 daughters instead of 1, so it takes more time. I think, let's see. Daughter product may be radioactive or random, yeah, it is about daughter product. Because it produced, instead of 1, it produced daughters. هنا he just suggest why the total activity of the radioactive source measured at the time calculated may be greater than 0.40. Because we have only 1 lanthanum, which is decayed into 1 or more. So each one may have more activity than this value. يعني أنا بعمل releasing ليها more stable أو less active, which undergoes a chain reaction to another one until we reach the stability. عشان كده we have we called it daughter atom يعني atom أو ايزوتوب منبثق عن الايزوتوب الأصلي. فممكن يكون راديو اكتيف او ممكن يكون ليس راديو اكتيف، فانت ما تقدرش تجزم ان هي اللي هتكون الاكتيفيتي هي الفاليو دي، لانك ما انتش عارف اللي بيسايد للي هيحصل له ديكي هيطلع مين، لانه راندملي. عمليه الراديو اكتيف ديكي هي عمليه راندوم، انا ما ببقاش عارف هو اللي طالع ده طالع راديو اكتيف ولا هيحصل له تشين رياكشن ولا هيعمل لي على طول ديكينج لمور ستيبل. عشان كده I think daughter product may be radioactive or random nature of decay. فممكن يكونوا radioactive او ممكن يكون اصلا الراديو اكتيفيتي بتاعتهم اقل فهيطلع هي الفاليو دي اللي هو احنا بنسميه الباك جراوند ريموفال. يعني انت بتحسب كده من غير ما تقول ان في الباك جراوند حاجه، فانا عارف ان مثلا اللي هيطلع من بس اللانثانيوم ده هو ال 0.40 بس طلع بيسايد لي حاجه ثانيه، دي ممكن ما تكونش ليها راديو اكتيفيتي فساعتها تبقى ال 0.40 او يكون ليها حاجه ثانيه فتزود الراديو اكتيفيتي.
اوكي تمام.
اوكي you get it?
Yes.
اوكي I think it is enough ان احنا حلينا بس شويه حاجات، لان البي اي تي ما عليهاش اي examples، بس I'll try ان انا الاقي examples على البي اي تي، لان هو الجزء ده هيكون theoretical اغلبه، مش هيكون ليه اسئله. هو الجزء الميديكال ده اكيد هيكون كله بس ليه علاقه بالالتراسونيك والاتنيويشن والاكس راي بالاتنيويشن والسي تي سكان، والبي اي تي هيكون اكيد حاجه منهم، واكيد البي اي تي ولا هيجي مش السي تي سكان يعني لانه جديد. فهحاول اشوف في بيرسون ايدكسل اسئله على البي اي تي واحاول اشوف الشكل بتاعها، وممكن المره الجايه ان شاء الله ناخد سؤال او 2 قبل ما نبدا في الكوزمولوجي بارت او الجزء بتاع الاسترونومي. في مشكله في البي اي تي او في اللي احنا قلناه؟
No sir, no.
محمد
ناصر ما في مشكلة.
طيب ممكن يوم السبت انا هكون مسافر اسكندريه. احنا ما بناخدش السبت صحيح؟ لا انت تمام. يوم الاحد ميعادنا عادي زي ما احنا ان شاء الله. ممكن يكون الصبح بدري او ممكن يكون في ميعادنا عادي according للوقت اللي انا هرجع فيه، بس I think ان انا هرجع متاخر. فلو كده ممكن ناخد حصه يوم الاحد بكره الصبح لو انت فاضي، او ناخدها لحد في ميعادها علشان هكون في اسكندريه السبت فهرجع بالليل. ممكن لو وصلت الصبح هناخدها الصبح او هناخدها لحد في ميعادنا الساعه 4 عادي.
السر عادي لو بدك العصر عشان ترتاح مثلا يعني ممكن عصر no problem.
خلاص اوكي ان شاء
اللي
الله.
بريحك استاذ.
ان شاء الله. انا كده كده هبعت لك الانفيتيشن وانا في الباص، لو حسيت ان انا هاجي بدري هبعتها لك في الباص، لو حسيت ان لا الوقت هيتاخر هبعتها لك في ميعاد العصر عادي.
اوكي سر تمام.
ماشي.
شكرا
اشوفك
استاذ
على
يعطيك
خير.
العافية.
العفو ربنا يخليك.
مع السلامة.
الله يسلمك.